Let's have a look at atoms and matter. So this you should know from year 10, but let's go over it just to refresh your memory. The states of matter. So all atoms are in a continual state of motion, and there are 3 states of matter: solid, liquid, and gas. Now the solids, the atoms are tightly packed and they're vibrating on the spot. So think about an ice cube, really cold, not a lot of energy, just sitting together and they're shivering. Now a liquid, the atoms in a liquid are very loose and they flow over the top of each other. And in gases, they have high amounts of energy. So they're far apart, they're really active, they're bouncing across the room. So here's just a table that kind of gives you a rundown on all the 3 states of matter. So solids, they have a definite shape, a definite volume. Again, think about an ice cube. In the case of a liquid, with its shape, it'll always take the shape of a container. So whether it's a long, tall cylinder or it's your bathtub, the water will always take its shape. It has a definite volume and it's quite difficult to compress. Gases, on the other hand, they take the shape of the container as well, but they can expand to fill the volume of a container. And they're easily compressed. So think about a diver going underwater with his little scuba tank. He's compressed that oxygen into a small container. So changing states. So matter can change states because of temperature. It's a measure of the average energy of the particles. So an increase in temperature means an increase in energy and an increase in the particle motion. So think about the example before of a solid ice cube. Not a lot of energy staying in its little compacted cube. But then as that ice melts, its temperature is increasing, it's getting warmer. It changes to a liquid state, it's a higher amount of energy. They're flowing across each other. And then if the temperature increases enough, you can get that water evaporating into gas, which will be high energy. Now we can also do the opposite when we decrease the temperature. So if we were to take gas vapor to a liquid to an ice cube, we're decreasing the amount of energy and we're decreasing the particle motion. So let's have a look at the subatomic particles. You should all be very familiar with these. Inside the nucleus, we have our protons and our neutrons. And orbiting our nucleus, we have our negatively charged electrons. So the diagram I have here is of a carbon atom. So we should hopefully know that a carbon has 6 protons and they're in the nucleus, and it's got 6 neutrons and outside the 6 negative electrons. So again, I'll stay with carbon and let's have a look at how it's structured on the periodic table. So this again you should be familiar with. The top number is the atomic number. Then we have the symbol in the middle. The element name, now not all periodic tables will give you the element name, but in this case we've got one here. Then we have the atomic weight down the bottom. So it's important to remember the atomic number is up the top, atomic weight is down the bottom. So the atomic number, what is it? Basically tells us the number of protons inside this atom. Now protons are positively charged, and with all elemental atoms, so like this carbon from the periodic table, we'll know that it's a neutral atom. So we'll know that if there are 6 positively charged protons, there must be 6 negatively charged electrons. So the atomic number can tell us the number of protons and, because of that, the number of electrons. The atomic mass down the bottom is the weight of the nucleus. Now inside the nucleus we have protons and neutrons, but this weight doesn't discriminate. So if I want to find out specifically the number of the 3 types of subatomic particles, I need these 2 numbers to do the calculations. So if we start with protons, I can use the atomic number up the top to tell me that there are 6 protons. Now for electrons, it's pretty straightforward as well. If there are 6 positively charged protons, I must have 6 negatively charged electrons to have a balanced atom. So I know that the electrons have to be 6. So to calculate how many neutrons there are, we've got to do a little maths. And the easiest way to do it is to take the atomic mass, which is the number down the bottom, and subtract it from the atomic number up the top. Now why would we do that? Well, the atomic mass is the number of protons plus neutrons. I know how many protons this atom has because of the atomic number. So I simply take the atomic number away from the atomic mass, and that'll leave me with the number of neutrons. So if we look at carbon, proton 6, electron 6, neutron 6. Nice and easy to remember. So you should be able to do this with all of the atoms on the periodic table, just with the periodic table. You shouldn't need anything else. So let's have a look at isotopes. Now we'll only cover this briefly because you cover it in more detail in your HSC topic. So an isotope is essentially an element with a different number of neutron, but the atomic number will always be the same. So let's have a look at carbon again. So in this state we have carbon-12, which is the naturally occurring carbon that you see practically everywhere. It's very stable. It has 6 protons, 6 neutrons, and that's where you get the 12 from. So the 13 here is representing the atomic mass. So in this case, carbon-13 still has 6 protons, but it's got 7 neutrons, and that's what makes it an isotope. So it's got that 1 extra neutron. Carbon-14, which is the radioactive form of carbon used in carbon dating, has 8 neutrons, still 6 protons. So it's about as much detail as you need for this topic, and like I said, you'll go into more detail with isotopes in the HSC course. So let's talk more about atomic weight. Now the mass of an atom is weighted according to its abundance of naturally occurring isotopes. So that can be a bit confusing. Well, let's look at carbon. Carbon-12 is the most naturally occurring form of this isotope. 98.89% of all carbon is in the form of carbon-12. So in this case, the 6 protons, the 6 neutrons. Carbon-13, 1.11%. So it's not there as well. We don't talk about carbon-14, okay, because it's there in such an infinitesimally tiny amount and it decays and it's complicated. We'll talk about that one later. So let's just focus on the 2. So to calculate the atomic mass, because that can be a bit tricky. Why is it carbon-12 when on the periodic table it's 12.011? So this 0.011, this is coming from the percentage of the carbon-13. It's in a very small amount, so therefore it hasn't made much impact on the weight. But here's how it's calculated. So we take the percentage of abundance of carbon-12 over 100, because we want it's a percentage, times it by 12, and then you're adding that to the percentage of carbon-13 times the 13, and that's giving you the relative mass. So that's why all the masses on the periodic table are in point form. To make it easy for you guys, that's why we get rid of these points and we just say that the mass of carbon is 12 when we do our calculations. But it's just a bit of info to show you where that number comes from. So let's look at electron configurations. We use most typically the Bohr model, which is the picture here, and that was created by Niels Bohr in 1913. And what it's showing is the electron shells and how the electrons are placed. Now, to calculate the maximum number of electrons on each shell, we use this equation right here, 2 times n squared. Now, n is representing the shell number. So if we have a look at this diagram of lithium, the first circle would be shell 1, the second circle would be shell 2. So I've made some calculations here. So it's n1, so that's shell number 1. So we have the 2 times 1 squared, which gives you 2. And that tells you that the maximum number of electrons that can be on this first shell is 2. Let's calculate it for shell number 2. So shell number 2 times shell number 2 squared will give you a maximum number of 8. Now lithium doesn't have 10 electrons. It's only got its little 3. So it'll fill up its first shell with its 2, and then its third will move up a shell onto the second electron shell, and it's quite happy to float around there by itself. So let's have a look at some other elements. So here we have sodium. It has 11 electrons. So on its first electron shell, it'll stick with its maximum of 2, move up to 8, where 8 is the maximum. Now let's do the calculation for the third shell. So it's 2 times 3 squared, and that's a maximum number of 18. Easy to fit, it's 1 electron. So to make it easy, we write the electron configurations like this, 2, 8, 1, and we put it into brackets. So you might see, you might have the element symbol Na, and then you might see this next to it, and that you know that this is the configuration for its Bohr model. So let's have a look. Let's increase it to 18 electrons, 2, 8, and on the third we have 8. Now, this is where it can get a little tricky, and I am going to go through this again in class, but I'll try to take it slow. When we stick to the equation here for the third shell, so if it's 2 times 3 squared, that equals 18. You would think that when we move to potassium 19, that the electron configuration would be 2, 8, 9, because the maximum is 18 on shell number 3. But that's actually not the case. Let's have a look. First shell 2, second shell 2, third shell 8, fourth shell 1. What's going on? Shells like to be balanced, and 8 just happens to be the number that shells like to be balanced at. So when we have a look at this electron configuration, at shell number 3, it goes, you know what? I've got 8. I'm happy. Go to another shell. I've got my 8. I don't want you. So shell number 4 goes, well, all right, fine, I'll take it. So when we look at potassium, the electron configuration becomes 2, 8, 8, 1. When we move up to calcium, shell number 3 does the same thing and says, you know what, I've got my 8, I'm happy. Go to the next one. So the 20th electron also goes to shell number 4, and it gives you the equation 2, 8, 8, 2. Now, this is where it gets even more complicated. 21. Now you'll have a look here. Shell number 4, rather than being balanced at 8, says, you know what, I've got 2 here. 2's enough for me. Go back to 3. Okay, I've had enough of you. Don't give me your leftovers. You keep taking them. So shell number 3 goes, all right, I'll take it. So the electron configuration changes. 2, 8, 9, 2. And as you can see from the rest, it'll keep taking them until it reaches its maximum of 18. So when we did that equation, 2 times 3 squared, the maximum number that shell number 3 can take is 18. So what happens? It starts with 2, 8, it'll balance at 8, send 2 to electron shell number 4, then go back to 3 and fill it up to 18. So we can have a look here at 31 at gallium. 2, 8, 18, it's full, so it's sending everything else to electron shell number 4. And if we do the maths on electron shell 4, 2 times 4 squared, the maximum is 32. So it'll keep filling up shell number 4 until it reaches 32 before going up to the 5th shell. Okay, I hope I haven't blown you away too much by that. Again, I will go through it with Bohr models in class, so it's a little clearer to understand. But watch the video a few times. Make the Bohr models yourself and see if you can work yourself around it. So, what do you do now? Again, watch the video a couple of times, especially the calculation of atomic weight if you've forgotten how to do it from year 10. The electron configurations will also help because that is a new concept for you. So practice doing the Bohr models yourself. Complete the quiz and I'll see you in class.